Did you just start recording?
Did you get the Zoom link from the form or from the email?
Me?
Yeah.
From the email.
Okay, let me double check.
Is it working? Anushka?
Hold on, let me double check. I'm trying.
Hi,
Hello.
how are you doing?
Hi.
You well? How are
Good.
you?
Good.
More people should be rolling in shortly.
Oh, you got that nice graphic. That's great. I think one of my grad students, Chuck Manso, put together some of these graphics.
Hello, everyone. Thank you for coming. It is 4 o'clock, so we will just about get started. Sorry, I'm at school. I might be a bit noisy in the background. Alessandra, did you want to share your screen?
Yes, I do that. Just tell me if you can see the speaker notes when I'm sharing my screen.
So do you want me to share the screen now, or you're sharing now? Okay, great. For the
Is
title.
that
Alessandra's got it. Okay. Do you want to head over to the next slide?
yeah?
Okay, so just a couple of things before we get started. You are free to ask questions during the lecture. And also we will definitely cut the lecture off at 5:30 to respect everyone's timing. So be sure to get your questions in before then. And with that, let's get started. Alessandra, feel free to take it away.
Okay, so today we're going to be talking with Jonathan Wurtele, who received his BA in Physics and Math in 1979 and his PhD in 1985 from UC Berkeley. He was a research scientist at MIT's Plasma Fusion Center from 1984 to 87, and assistant and associate professor in MIT's physics department from 1987 to 95.
He returned to Berkeley in 1995, where he is now a professor of physics, a fellow of the American Physical Society, and has been a foreign research fellow at the Institute of Space and Aeronautical Science.
He shared the John Dawson Award for Excellence in Plasma Physics Research in 2011. He is a member of the ALPHA collaboration, which synthesizes and conducts precision physics measurements on antihydrogen.
And beyond plasma physics, he has worked on the Berkeley Earth Temperature Study and spent a sabbatical at the New York University Center of Urban Science and Progress. So with that, please welcome Jonathan Wurtele.
Thank you.
Well, thank you very much for that nice introduction. It's a pleasure to be here and to talk to you all. And I look forward to giving this talk. And as was said, please interrupt me. If you have questions, just ask away. It's very informal, and I like having questions, so please ask away. So I will, I can't share because somebody has to let me share.
Yeah. Hold on, Alessandra will make you host. The
Okay.
version of Zoom we're using doesn't allow us to have co-hosts. One moment.
Okay. You don't get professional Zoom?
You should be able to.
I can share, sure. We're good. Okay, let me share this. And I'll start my talk and you'll tell me if you see things correctly. Participants can now see your screen. That sounds good.
Yeah, we can see it.
Play from current slide. Are we good?
Yep.
You see the full slide, right? Occupying the full screen?
Yes.
Yeah.
Great. Okay, so as I said, please interrupt me. I'm really speaking not just for myself. I'm speaking for the Alpha Collaboration, which is about 40 people. The population changes slightly and people come and go when students graduate, for example. And what we started back in 2005 is trapping antihydrogen. So I will tell you something about antimatter, what the anti-antihydrogen is about. Then I'll tell you how we trap it, why we trap it, and what we've discovered so far, and finally, what we hope to do in the future. And I don't really have 89 slides. There's a lot of backup there. So don't get scared with the numbers. Okay. So what is antihydrogen? In hydrogen on the left, what you see is the electron going around the proton, at least in the cartoon of an atom. On antihydrogen, you take the antiparticle of the electron, which is a positron, and you combine it with the antiparticle of the proton, which is the antiproton. So the charges of each particle got reversed. But in principle, if you can create antihydrogen, and creating it was, of course, the big trick here, you will be able to make this perfect anti-atom and compare them. In the cartoon, of course, they're doing exactly the same thing, but in the real world, until you do it, who knows? So in outline then, I'll first discuss antimatter, some motivation, give an overview of how you actually trap these things. I'll talk about our first precision experiments and our plans for the future. So really, antimatter begins with Dirac. Dirac, in 1928 to 1931, wrote papers in which he took the ideas behind quantum mechanics and the ideas behind special relativity, so Schrödinger, Heisenberg, Dirac doing quantum mechanics, and Einstein doing special relativity. He combined those ideas together, and he came up with an equation, appropriately named the Dirac equation. He then solved his equation, and he found out that not only was there a solution which corresponded to an electron, which is satisfying an equation that obeys special relativity and quantum mechanics, but there's another particle which would have a positive charge. And he therefore said, rather than think this is a mathematical artifact, he said, well, this might be a new particle. It could happen. My equation allows it. Why not? Okay. As I'll just read, a hole, if there were one, would be a new kind of particle unknown to experimental physics, having the same mass and opposite charge to an electron. We may call such a particle an anti-electron. And this was the first time ever that somebody had used a mathematical equation to predict the existence of a particle. Until then, there were, people did experiments, there were particles, they argued about atoms and charges and the like, but nobody had actually written down an equation, looked at the solution and said, hey, that solution corresponds to a particle that's never been seen before. This was an unbelievable thing to make this prediction in 1931. Predicted. So how did he predict it? Well, he took quantum mechanics and relativity. The equation describing the electron had two solutions, and one of them just wasn't an electron. So he hypothesized the existence of a new particle, the positron. And not only that, he is memorialized. If those of you who've been to London, that's Westminster Abbey on the left. And if you want to know what the Dirac equation is, you can go there and see his plaque on the floor commemorating his discovery in Westminster Abbey. And that is the Dirac equation, that I gamma dot, that funny symbol on psi, is equal to m times psi. 1984 is when he died. It's not when he wrote down the equation. Okay, so now, they're theoretical physicists, which is Dirac, and they're experimental physicists. Carl Anderson was an experimental physicist at Caltech, and he was studying cosmic rays. Here is a picture of him on the left. And he wrote a paper just a few years later in 1932 called The Positive Electron. So here is a lead plate, and the lead plate has a magnetic field, and you can see a line, which I'm about to show you in red. You see that line in red? That line in red corresponds to the path of a particle. It was a little harder to see, so I put it in red, overlaid it. And the bending direction is that of a positive charge. The bending radius is that of an electron. And from that, he concluded he had discovered the positron. So he discovered them in nature in cosmic rays, predicted but never previously discovered. Okay, so it's created in cosmic ray showers. You maybe know about cosmic ray showers. The energetic proton hits the atmosphere, it decays into a bunch of things. Can you see my cursor? Okay, decays into a bunch of subatomic particles, and eventually you get electrons and positrons coming out down here, and then that was what he discovered. So here's what a shower would look like conceptually. It also occurs rarely, but with not non-zero probability. If you eat a banana, you are slightly positron emitting for a bit. So banana will emit positrons, as therefore will you if you consumed that banana. Positron sources can be made in accelerators. You take some element that was not a positron emitter, you irradiate it, it becomes a positron emitter. This is where we get our positrons from a source that was prepared in an accelerator. They're also used in positron emission tomography. That's PET. And what you see is the positron emission of a person who's consumed some positrons for a medical procedure. And you see the emission, and where it's abnormal, then they can make some diagnosis and hopefully provide correct medicine. Okay, now physicists, when they see a good thing, they keep going. So you have the anti-electron, the positron, which was predicted. Why not an anti-proton? Well, indeed, why not? Well, it took, as you see, 1928 to 1932, about 4 years to discover the positron. It took another 23 years to discover the anti-proton. Where was the anti-proton discovered? Right here in town, in Berkeley, at Lawrence Berkeley Lab, at the Bevatron. I'm not sure any of you, have any of you visited Lawrence Berkeley Lab? I can't see raised hands. Some of you may have visited. You may actually know where the Bevatron is. So here you can see Segre and Chamberlain, who won the Nobel Prize for this discovery, along with Wigrad and Ypsilantis. Observation of antiprotons, 1955. And in those days, of course, science is very competitive. You want to tell your friends, but not make public announcements until the time is ready. And so they made a little blackboard here. Progress of the antiproton experiment. Note all results are provisional and subject to recall. Keep them, quote, in the family. So this is how they said, keep a secret. And you can see the date. And so this is actually when they actually discovered it, is that somebody took a picture of their blackboard. Okay, so that was the World Wide Web in 1955 with somebody's blackboard. So why study antihydrogen nowadays? So antihydrogen, then you could make its constituent particle. Let me go back a second. Why did it take 23 years to make the antiproton, whereas it just took a few years to discover the positron? The answer is that positrons occur naturally. You can see them in cosmic rays. Anderson went out and found one. Antiprotons don't occur naturally. You have to create them in the laboratory. The way you create them is you take a proton that's energetic, so you accelerate it, and then hence at the Bevatron. Beva was BeV, which is now called GeV, so billion electron volt accelerator, Bevatron, took protons to a few billion electron volts, they hit a target, and they created, among other things, antiprotons, which were then discovered by these guys. Okay.
I have a question.
Yes.
Why is it that the positrons occur naturally in nature, but the antiprotons do not?
It's I guess the energetics of it. To make a positron, you don't need as much energy as you need to make a antiproton. So the positron can occur naturally in some decays, but there isn't the energy in those decays to make the antiproton. Would be the answer. Of course, it's a big, as I'm about to say, but just to get ahead, you might imagine that in the Big Bang you had equal numbers of antiparticles and particles. I mean, why not? At some abstract level, there's an equation, there's a Big Bang, the equation has symmetry between positive and negative solutions. Why not 50-50? Well, it's very much not 50-50, and it's one of the big questions that maybe we'll shed some light on someday. I can't read the chat, so if somebody has questions in the chat, please read them to me.
There currently aren't any questions in the chat, but I have a question.
Sure.
Do naturally occurring positrons impact like our environment at all?
Not in any deleterious way. They're used for medicine and the like, but the numbers of them that occur naturally, I mean, cosmic rays do occur, and positrons are part of cosmic rays. There are a lot of stuff, and people think maybe some genetic mutations occur from cosmic rays. So, but that's a natural thing. We've evolved with that. Therefore, I wouldn't say it's necessarily a negative thing. That's just how people have evolved. And so there are cosmic rays in the environment, and maybe some cosmic ray comes in and mutates somebody in some way. Maybe that's bad, maybe it's good, I don't know, but it is a natural occurrence. So it's not like you have a radioactive area, like a uranium mine or something, where somebody would go in there and get really sick. They don't occur at that kind of levels. Okay, so there's something called CPT, which is motivating us. CPT stands for charge, parity, and time. And I'll explain each one of those separately. The physical laws, as we understand them today, don't change under what's called a CPT transformation. What we're looking to do is break, if nature, we're not looking to break it, but we're looking to see if nature breaks it, CPT, because that would break something very fundamental about the construction of physical laws. It wouldn't affect everybody, and your life wouldn't change, except maybe intellectually, but it would be an interesting thing for physics. So how would you look for an exception? It turns out one way to find an exception is to look at, so here as an artist's conception is the spectrum of hydrogen and the spectrum of antihydrogen below it, frequency, and then the lines, the colored lines here representing different lines of the atom, radiation lines. And so if they're different, if one of them is different, then that would break CPT. The spectrum of hydrogen is known to a part in the 10 to the 18. That's 1 in a billion billions. Antihydrogen, we're still a long way from that, but we are getting better and better at making our comparisons. Okay, what is this CPT? So C is charge conjugation. Take something which is plus, make it minus. Take something minus and make it plus. Times is time reversal. So here you see, this is going to be a cartoon of a metronome with just two things, two blocks, two spheres. The collisions would be conservation of momentum, that's the first equation, and conservation of energy, that's the second equation. So let's see if this plays, it should play. So here you see it's bouncing one, it's not completely symmetric because the masses are different. But now we can play it. And now we can play the time reversed version of it. And you don't see the difference. So basically, if two particles collide together, you don't know which direction you've seen it in. Time going backwards or time going forwards. Okay, so all elementary interactions, with the exception of things that I'm about to talk about, would have time reversal. So all of Newtonian mechanics has time reversal. You might wonder, how come you're getting older if everything is time reversal, right? You can tell that you're getting older, not younger. So why is that? Does anybody know the answer, by the way? If every elementary interaction is time reversible, where are you getting older? Well, it's the same reason, even though if I stir cream into tea, it's obvious what direction time went, right? So you can take a lot of these elementary things which are reversible, but you combine them in ways that involve increasing entropy to make it look irreversible. Okay, so that's a nice physics topic for your future. Parity is going from left to right. So coordinate x goes to minus x. You see a left hand and a right hand. That's a parity transformation. You could also combine charge and parity. So that would be turning the black and white would correspond to the charge and the parity would correspond to left and right. You could do C, which would be just interchanging black and white, or P, which is left and right, or you could do CP, which is moving along the diagonals. So C.S. Wu, who I'll tell you about in a minute or two, discovered that parity is not conserved by the weak interaction. Left-handed is not the same as right-handed. CP was thought to be conserved, but found to be violated by Fitch and Conan. Was found to be violated by Fitch and Conan, got the Nobel Prize. In case I forget to say it later, the omission of C.S. Wu for a Nobel Prize was a huge mistake of the Nobel Committee. And everybody thought so at the time and thought so afterwards, but that is what happened. So if you add time reversal, then you take particles, you change their charge, you switch left to right, and you make time go backwards. That's a CPT transformation. And CPT should hold for any locally relativistic quantum field theory. Fancy words. It means that the equations we use to describe the elementary interactions all obey CPT. So any violation of that breaks those equations. Okay, here is C.S. Wu, also known as Madame Wu, with her parity experiment. So she's at the controls of her experiment. She was a Berkeley graduate student. She worked closely with Lawrence and Segre in graduate school here. She was heading to Michigan, but she stopped luckily in Berkeley, and we grabbed her before she could get to Michigan and offered her a position, and she stayed here. She had all sorts of troubles later. Not every place was hiring women, but she was so smart and so well respected that she ended up in Columbia and had a fantastic career. Her experiment for parity violation basically had the following logic. You don't have to understand the details of that cartoon on the right, but just the following idea. She came up with an experiment where what's called you would take an element which would beta decay, in other words, it would emit an electron and then turn into something else. You would align the spins of this element in one direction. If you did a parity transformation, you'd get the thing in the mirror, which would look different because those red lines are going around in a different sense with respect to the directions of the emission. Okay, so the only way you could get a system which conserves parity would be if the emission of those beta rays was spherically symmetric. So that was the essence of the experiment. If what she discovered was not spherically symmetric, then parity was not conserved by the beta decay process, but also known as the weak interaction. Okay, and this was a major surprise to physicists. I mean, it's a huge surprise because in the electromagnetic force and gravity, parity is conserved. So here you have a force which doesn't conserve parity. There's C.S. Wu in Berkeley. Okay, so physicists have been wrong before. Wolfgang Pauli, who was one of the brilliant physicists of the 20th century, didn't hold back. I do not believe that the Lord is a weak left-hander, and I am ready to bet a very high sum that the experiments will give symmetric results. Well, he lost his bet. Lev Landau, that was on P violation. Landau is one of the great Russian physicists of the last century. If CP is violated, I will hang myself. Okay, well, he didn't do that, but it was violated. So CPT symmetry, everybody believes that it's going to be preserved, and it may well be preserved in our experiments, but until you test it, you don't know. And what you see from C.S. Wu's experiment is that there's an idea, you test it, you see what happens. It's an experimental science. Nature decides, not what some theory says. All our results today are consistent with CPT. An electron and a proton versus a positron plus an antiproton. CPT says with the same spectrum, and the weak equivalence principle says the same gravitational force, and that's what we're planning to do as gravity. I'll tell you about that at the end. Another reason to study it, the Big Bang should have produced equal amounts of matter and antimatter. The imbalance is 1 part in 10 billion. That's us. We're the lucky imbalance here. But why? Nobody knows. It's one of the big questions of physics. Why the imbalance? Okay. Maybe we'll shed some light on that. Antimatter. So what are we doing with gravity? You know that an apple falls to the earth. Tom Roberts made this nice graphic. Apple falls to the earth. We expect an anti-apple would fall to the anti-earth, but we have no way of knowing that. But we have figured out how to do the following. To measure if the anti-apple, in this case, antihydrogen atom, not a real apple, would fall to our Earth. And it should be exactly the same. So this should be the same as the apple. Oops, went too far. Okay, I have a interlude. How many of you have seen Red Angels and Demons? Anyone? Our experiment was part of the motivation. Like, can you hear this?
Number 86.
It's wireless. It too was stolen. It could be anywhere inside the Vatican.
That canister contains an extremely combustible substance called antimatter. We need to locate it immediately or evacuate Vatican City.
I'm quite familiar with incendiaries, Miss Vetra. I've never heard of antimatter being used as such.
Well, it's never been generated in significant quantities before. It's a way of studying the origins of the universe, to try to isolate what some people call the God particle. But there are implications for energy research.
God particle?
What we call it isn't important. It's what gives all matter mass, the thing without which we could not exist.
You're talking about the moment of creation.
Yes, in a way I am. The antimatter is suspended there, in an airtight nanocomposite shell with electromagnets on each end. But if it were to fall out of suspension and come in contact with matter, say at the bottom of the canister, then the two opposing forces would annihilate one another violently.
What might cause it to fall out of suspension?
The battery going dead, which it will, just before midnight.
Kind of annihilation. How violent?
Sorry.
A cataclysmic event. A blinding explosion equivalent to about 5 kilotons.
Vatican City will be consumed by light.
Okay, so that's it for the Vatican City. It's kind of a fun movie. When we first started this project, some people in Berkeley were unhappy that, in fact, we were off on some warmongering thing with antimatter. However, I can assure you that the amount of antimatter we make is not enough to do any harm, and you do not need to worry about that. Okay, so if you want to buy some antimatter, somebody in Brooklyn will sell it to you. Here's a little container, but that, of course, is fake. Antimatter can only be confined in a can with no material walls. If the antimatter hits the material wall, matter, it turns into energy, turns into light. So you lose your antimatter. So you have to confine it within a can made of electromagnetic fields. So they have to be strong enough to confine the particles. And in fact, since we start off with positrons, which are charged particles, and antiprotons, which are charged particles, we actually have plasmas. Okay, neutral antihydrogen is confined by its magnetic moment and magnetic well. Technology limits the depth in temperature units to about 0.5 Kelvin, which is a very, very low energy system. When the antimatter hits the walls of our detector, we see it. We can see a single antihydrogen annihilate. So if we do something to antihydrogen that makes it say, ionize, then we see the antimatter hit the wall. Okay, so we can now make, 70,000 in a year. So the history was that, a couple of them were made at high energy in 96. Don't worry about the numbers. They were made relativistically, not very useful. 2 experiments created cold, but still too untrappable antihydrogen in 2002. But you need cold trapped antihydrogen to do it. And this is what we did. So where do we do this? We do it at CERN. This is a picture of Lake Geneva on the right. The airport, Geneva Airport, is down here at the bottom right. The big red-orange curve here is the Large Hadron Collider, the LHC, 27 kilometers in circumference. This little thing here is just a feeder to the LHC coming in like this. Down here is the Atlas detector, where a lot of my colleagues work. And then the whole thing starts with smaller accelerators. So it's a chain in which a small accelerator produces some particles, which go into a bigger one goes into this SPS, and then finally into the LHC. If on the bottom right then, so now here's, to give you perspective, the red in the top right here is what you saw before. That's just the circumference of the LHC. Down here is CERN. And here, right in the middle of this photo, is the Antimatter Factory, the AD. And that's where we do our experiments. The reason we do them there is that CERN is the only place in the world that knows how to, that has the, not the know-how, but has the technology to produce low energy antiprotons that we can then use. They're produced at high energies, maybe 1 billion electron volts, and we take them from them now at, say, at 1 million electron volts, and we have to go down to 10 to the minus 4 electron volts. So while all of CERN is busy accelerating, we're busy decelerating. We make things cold because atoms don't function when they're cold, they don't function at high energy. This is a picture of the experiment. It's much more cluttered now, and we succeeded. We also made some land grabs, so we're a little bit bigger than this picture shows, but you can see the setup. Top left here is the antiproton source. That's a radioactive source. Comes this way. The antiprotons come from CERN, coming in here. And then in here is where we create antihydrogen and study it. Okay, so what does our setup look like now? As I said, we had a land grab. Before we had maybe this much space. We made it bigger. It's about 30 feet. And antiprotons coming from the left, the positrons coming from the right. We have this trap, what's called alpha 2, which is where we do our precision physics experiments. And we have our gravity trap. A lot of the gravity trap work was started at Berkeley, actually, the ideas behind it. And then later our collaboration really caught on. The Canadians got a big grant to do it. And we have a very big experiment coming online here, at least big for us. It's still small compared to anything CERN does.
I have a question.
Yes.
I read that the way you cool down the hydrogen is through laser cooling. Could you explain how that works a little bit more and how it actually helps cool down the hydrogens?
Yes, I will. I'll get to that right after I get to how we make it. I'll talk about the cooling.
Okay.
Let's see. Sorry, this. Okay, can people see the movie?
Yes.
Okay, so this is a cutout of our experiment. Inside this region here is where we would create the magnetic field, and what you're going to see is kind of an unfolding of our apparatus. So in here is where the antihydrogen is studied. Outside are these 3 layers. That's a detector, which detects the antiprotons will hit it. If, for example, we ionize the antihydrogen, it hits the sides and will be seen by the detector. So I'm going to peel open the detector here. momentarily. Here the 3 layers are being peeled off. So now you see the magnets, the octopole, the mirror coils, the annihilation detector. The octopole and the mirrors are needed to trap antihydrogen, which is trapped because it has a magnetic moment a bit like a bar magnet. Inside the octopole, which we're about to look in there, so these are just the currents that energize the octopole. The mirror coil provides confinement of antihydrogen along the direction of the tube, and the octopole perpendicular to the direction of the tube. So now we look inside. Inside are a bunch of electrodes. Those are those cylinders that you see. And those cylinders are used to take the positrons and antiprotons and control them. So you have charged particles. You can see the antiprotons and the positrons are naturally a different, okay, let me just stop here for a second. An antiproton, so this is the red curve is the electric potential. Think of that as a plus or minus. Okay, so if it's high, that's like a positive potential. So the positrons will want to go away from that. And the negatively charged antiprotons will like the high potential and will tend to be up here. But how do you make antihydrogen? You're stuck. Your positive particles are down here, the green, and the antiprotons, the purple, are up here. That's no good. You have to find a way to manipulate these potentials to make them overlap. When they overlap in the right way, you can make antihydrogen. So eventually, we will get them to overlap through our manipulations. The details don't really matter much. Now they're overlapping. And once in a while, so that might have been 10 million 10 million positrons with 10,000 antiprotons, you make an antihydrogen like this. In our first year in 2010, we made 7 of them all year long. And now we make 70,000. The antihydrogen, that's the H bar, is confined in a magnetic potential. That's just like think of these hills here in the red underneath. We then lower those potentials and they hit the wall. When they hit the wall, they decay and we see them. So every time something decays, we can see it. And by studying those decays, according to what we're doing or not doing, we can understand what we've done. So as an example of what we do, microwave spectroscopy. You shine microwaves on antihydrogen, you can change their magnetic moment. It doesn't matter what the magnetic moment is for the purpose of this discussion. It's a property of the antiatom spin. We can flip it. And when we flip it, it's going to hit the wall. So it flips at certain frequencies. We can control it. And it can be trapped in one direction. And then we flip it to an untrapped direction. Now it's not trapped. And it's about to hit the wall. And then we see it. So by looking at whether or not we flip that magnetic moment has to do with the frequency of the microwaves. We know what would happen with hydrogen. We do the same thing with antihydrogen and we see how that works. Okay, and this was nicely produced by some group. Okay, energy scales. Given the time, I don't think I'm going to talk about this a lot. I just want to say that we really need to cool things to low temperatures. And currently we can make antihydrogen that is, the average temperature is maybe twice the speed of a Major League Baseball pitch. Okay, so that's pretty slow. And with laser cooling, we're going to get to slower than that. So that's pretty slow. Okay, so we need to take antihydrogen. We need to study it. It needs to be around for a while. We actually make it at some excited state. You know, atoms have excited states and then they radiate, they give off light, and they go to their ground state. 1 second is enough for that. We first trapped for 1,000 seconds. That was enough to get coffee and come back, about 15 minutes. We can now trap for 36,000 seconds. It's 10 hours. And ultimate litter, we tend to do experiments after about 8 hours of accumulation. I just want to show this amusing picture here. When we first make them, in this first second before they get to the ground state, because there's a magnetic field which is used to control the charged particles, the atom is something called, we believe it's something called the guiding center atom. So the magnetic field is actually important in the structure of the atom. That's a very different picture of the atom from what you see, but this goes away in a second and we can't study that. Okay, this is showing that we've done really well in trapping. This must be something I showed to, somebody showed to a funding officer. When you want to get more money, you put plots like this together, show how well you're doing and ask for a little more money. This is the antihydrogen trapped per hour as a function of calendar year. And here you can see in 2010, it was less than 1 per hour. And in 2017 or so, it was up at 200 or 300 per hour. So, and we can trap them, we can stack them, you trap, and then you trap some more, you can stack over 1,000. And we had over 70,000 total that year. Okay, and the rest is just details. Laser cooling. Okay, this might be the article you saw, I'm not sure. This was an article, our most recent Nature article. Here's the pretty cover. And basically, the way laser cooling works, so let me just show the apparatus from it, describe what we do. So lasers come in, and we have cavities, there's room for microwaves and the like. So what we end up doing to cool is if you preferentially are absorbing or emitting photons according to the direction of the atom. So it's like a Doppler shift. So you know that if there's a car, if there's a siren, the siren will sound differently if the ambulance is speeding towards you or speeding away from you. That's known as a Doppler shift. That Doppler shift is used in laser cooling so that you will absorb preferentially if you're going one direction or the other. And that way you can take energy out of particles as they're moving. So the faster particles, you take some of the energy out and you laser cool. It's a little bit tricky how we pick the level. So there's a reason it took us 15 years to figure out what we're doing. Science, so my goal of showing you this is not to actually expect anybody to understand it in particular, but it's rather just to emphasize that in doing science, there's a lot of the great stuff, which is, coming up with a simple experiment, inventing the simple experiment. But there's also, to get something to work, is just a lot of details that people have to work through. This is just an example of some of the details you have to work through. In atomic physics, to know what you're doing. And physics does a lot of it. That's why it takes time to learn it. Okay, I'll just look for a minute. I'll say one quick thing about the protocol. So what you do is you would prepare a state. So you're doing an experiment. It's all these experiments kind of have the same flavor. You prepare antihydrogen in a certain state, and then you do something to it or you don't do something to it, and you measure the results. Okay, so we can measure, we know how to excite certain lines in antihydrogen. Okay, and we know that the spectrum will look different if the antihydrogen has a bigger spread in velocities or a smaller spread in velocities. And so depending whether or not you cool or you don't cool, you're going to see a different looking spectrum. That's essentially the idea behind it. And actually, so here's the example of the simulation and the experiment. So what do you take from this? On one axis is the relative frequency. On the other axis is the normalized counts. That's on the left, A and C, and B and D. You have the counts versus the time of flight, which is how long it takes it to hit the wall. The reddish curve is better in both cases because it means that in the time of flight is from when you do something to make it ionize, how long does it go to hit the wall? If it's going slowly, it takes longer. And so you see that it's taking longer in the red, which means it had a lower temperature. That 4.8 number represents the temperature, 4.8 micro electron volts, versus 20 micro electron mu is 10 to the minus 6 micro. So you had 20 looking in D, you had 20 micro electron volts here for the mean temperature and 4.8 here. That means it got colder. Similarly, your line width here got smaller. Okay, so that's showing you that you actually did some cooling. Okay, good. And here you see, this is our Nature paper from 2018. This is the spectrum of the 1s to 2s line in antihydrogen. And here's a similar line. So now this is data taken in 2021, and you can see the impact of cooling has made, that's the green curve here, has made this line narrower. So the cooling demonstrably changed the way in which we can do our measurements. And we hope by doing better cooling and playing some other tricks, we increase our precision by a factor of 10. Why am I talking about precision all of a sudden? We want to study CPT, seep charge parity time. You don't just do one measurement. Your measurement has a precision. And so far, we don't see any differences between hydrogen and antihydrogen. But so we say, okay, we'll look a little bit closer, and we'll look a little bit closer. And so right now, we're in the business of being able to look maybe a factor of 10 closer in the next few years. It took 15 years for us to figure out how to trap, how to cool, how to diagnose the antihydrogen. But now we're going to actually come up with the precision measurements at a factor of 10 better than we have to date. You might ask the question, I think this conceptually is an easy one to ask. So let me ask you, should antihydrogen have a charge? Anybody want to answer? I see shaking heads. Why not?
Because they're equal numbers of protons and electrons.
Right. So you would expect the same way that hydrogen doesn't have a charge, antihydrogen shouldn't have a charge. That would be the expectation. But maybe that's wrong. Maybe somehow some small fraction of the positron charge is not exactly equal and opposite to the antiproton charge. Who knows? Hydrogen is neutral to a very, very good high precision. Maybe antihydrogen is not completely neutral. That would be a shocking result. But in the same way we measure the neutrality of hydrogen, we also want to measure the neutrality of antihydrogen. So how would you measure the neutrality of, if you wanted to know if antihydrogen is charged, how might you measure it? Suppose the charge of the positron and antiproton were not quite equal. What might you do?
Put one in an electric field.
Yes, right. Put them in an electric field. So that's the little picture here, the cartoon of what we did. You put in an electric field and you see, does it go one? Can you do something? Can you manipulate it? If it has zero charge, you can't do anything. But because it's an experiment, you don't know if it has zero charge. All you know is it has charge less than what you can observe. And so you run computer programs. And this was graduate students, undergraduates are doing this, running computer programs to see if it had a certain amount of charge, would it do something? Our system's a little more complicated in this cartoon, but the idea is quite similar. So let's just see here. So normal matter, believe it or not, is neutral to the precision of 10 to the minus 21 times E. E is the charge of the magnitude of the electron charge. So 1.6 10 to the minus 19 coulombs. That's quite neutral measurement. CPT says that they should be exactly the same. You can't do it, so you can't measure antihydrogen the same way you measure hydrogen because of all the problems we've discussed. Prior limits were not very good. You could use superposition. Okay, maybe that's not, it's technicality here, but it's not important for this discussion. Okay, so we're going to see if it's testable with charge. It turns out, so the suggestion was to put on an electric field. we can't just put arbitrary electric fields because we have those electrodes, and if you put on too high a field, you'll short out the electrodes, and then your whole experiment might be dead because you have to take the whole thing out and fix it. So that would be very bad. So, but what you can do is actually kick it randomly. Oops, just a second. Okay, you can kick it randomly here. So what we actually apply is random electric fields. The gentleman on the right is Enrico Fermi. This is called Fermi Acceleration. It's believed to be one of the processes by which cosmic rays get their energy, is they're getting random kicks as the protons are running around in the galaxy, they get random kicks. So here you see an electric field which is never very big, but it's always randomly going one direction or another, and finally it goes out. And to some extent, this is the same way that if, okay, I guess I can make a joke with alcohol, right? Is anybody gonna get, no, it's not being recorded or anything, right? I'm kidding you. Okay, if I drink too much and leave the bar, okay, not you, somebody over 21, okay, and begins to walk randomly, take a step in one direction, a step in a random direction, so spin around, and each time you'll eventually get somewhere. You won't end up back at the bar, but your distance won't be the number of steps you take. It'll scale to the square root of the number of steps. That's a random walk. Okay, so what we're really doing in energy is giving this antihydrogen, if it had charge, its energy would increase like a random walk, and eventually it would escape from the trap. If it escaped from the trap, we would see it. If we apply these fields and see nothing, that means it didn't have the energy to escape, and therefore its charge had to be less than some value. Okay, that's the expressions. You got the idea, I think. So the charge is unlimited, 1 over the number of steps. Okay, and the potential on the trap. And so we did some experiments. Oh, cosmic background is negligible. Remember those cosmic rays from the very beginning? A cosmic ray can come down into our experiment. And how do you know that that cosmic ray is an antihydrogen or not? Your detector will go off. So if a background event from cosmic rays confuse you, that's what's called some kind of it's an error in your experiment. And so you have to account for that. You have to minimize it. And we do all sorts of things to minimize the impact of cosmic rays. Okay, so you do this, you then argue with your collaborators for, I don't know, 6 months, and finally you come up with a neutrality limit of about 1 part per billion of the fundamental charge. Okay, so that's basically says the orange curve, you can actually understand it. It's a logarithmic plot of the charge, but what it says simply is that if you imagine that it had a charge, which is here. So if you look on the horizontal axis, you see 1 here corresponds to 1 part per billion of the electron charge. So that's really quite precise, actually. If it had more than a part per billion, then with high probability, say it's out here, let's go all the way out to 2, with very high probability, okay, at 3, so this is 3, at 3 parts per billion with very high probability, none of the antihydrogen would survive if they had that net charge. So how do we know that? We simulate it by in our simulation, we allow it to be charged. We apply these fields because there's some randomness in the kicks. We do some stochastic, which just means random. We do a lot of trials, we do a lot of simulations. We come up with these numbers that way. We can we get to set the limit. And here we're basically setting it at about for 50%. Okay. So the limit is of order 1 part per billion charge neutrality. 0.7 if you want to go to 1 sigma. And that actually, if you then assume that the superposition holds, which just means you put one thing on top of the other, you separated them out, you'd be the same answer. It's an improvement in the knowledge of the positron charge itself. Okay, should we talk about gravity? So you remember what Newton said, of course, that things will fall to the earth, that all things have the same acceleration. Has anybody been to Pisa? No, it's in the chat, nobody in the chat, somebody's been to Pisa? So you know what, they have the Leaning Tower of Pisa, right? And you drop the things from Leaning Tower of Pisa, and so you drop a feather and a golf ball, they actually won't fall at the same rate because of air, right? But if you could evacuate a chamber and you let them fall, they would fall at the same rate. Okay, that's because the inertial mass of the object is equal to the gravitational mass, and you have force is m times a, which I assume many of you have been to high school many high school physics courses say F is equal to ma somewhere, and then they say that for gravity the force is m times g. So m times a is equal to m times g. Well, if ma is equal to mg, you cancel the m's on both sides, right? And the acceleration of Earth is just g, little g. That's familiar? But what you said was mass times acceleration, that's the force, is the gravitational force, which is mass times little g. Okay, what that says is that the inertial mass, that's the mass multiplying acceleration, is equal to the gravitational mass, that's the mass multiplying g. Is that true for antihydrogen? Again, this is an experiment. How do you know? This is how you would test if hydrogen and antihydrogen behave the same way in the gravitational field of the Earth. So at 300 millikelvin, that's our temperature, 90 meters per second. Again, a fast pitcher in Major League Baseball is around 40 meters per second, something like that. And we're going to get much lower. We'll get 10 times lower in temperature, or square root of 2 in meters per second. So we're down to baseball pitch temperatures for these antiatoms. You can't make a fountain. That would be to throw them up and see how long it takes them to come down. If you send them horizontally, it takes a long time for them to fall. That's doable, but we're not going to try doing that. We can find things magnetically. The gravitational force is weak, but we know that if we're careful, we should be able to do a measurement. So, will antimatter fall under gravity the same way normal matter falls? According to Einstein, and it's risky to bet against Einstein, but here we are, the weak equivalence principle asserts that it will. There are many theoretical arguments that say this should be correct. And here you can see the authors in parentheses after their arguments. But we're going to go ahead and do the experiment in experimental science. So this is the alpha G experiment in the alpha system. This is on the right, the detector. That's Dana Zimmer, was an undergraduate in the Fajan's Wurtele group. So Joel Fajan's my colleague and I worked together on this. Dana spent a summer or two in Geneva. And that's Hughes Landsberger. He's now a graduate student at Princeton. Dana's at, I think, San Diego. And this is the detector. It will go into this big cylindrical vault here. And we should have it running this year. Okay, these are some experiments. So again, the experiment we're doing is the one on the right. Does the anti-apple fall to our Earth? Basically, there are a lot of reasons, theory and indirect experiments, to say yes, but there have been no free fall tests. Nobody's done the Leaning Tower of Pisa test, which is what we want to do. Drop antihydrogen and see what happens. Okay, so again, that's just a summary of what I said. So here's the experiment we're going to do. We have that vertical trap. It's maybe 3 meters high, although we're probably going to have more like 1 meter between these mirrors. That's for starting. So here's an anti-atom. It's sitting there bouncing back and forth, confined by the magnetic field generated by the two coils here. You can slowly lower the field. And if gravity is the same as for hydrogen and antihydrogen, if you set these magnets to be exactly the same thing, you would expect that because gravity pulls this particle bouncing back and forth to the Earth, that as you lower the magnetic field, you're lowering both of them at the same time, your particle will tend to come out eventually at the bottom. Okay. Now we're really doing something slightly different. We're compensating for gravity and then we're comparing the rates top and bottom, but that's a detail. So basically, we're going to see if gravity is the same for hydrogen and antihydrogen. We already know, using earlier data, that the force on gravity is not 100 times little g on antihydrogen. The gravitational force of the Earth is not 100 times little g on antihydrogen. That's a very bad estimate, very coarse estimate. We hope to get down to a % of g over the next 5 years or so.
Does it,
Okay.
can I ask you a question?
Of course.
Does it make sense to ask if absolute zero is the same with matter and antimatter? Does it make sense to ask the question? Or?
Yeah, does it make sense? I mean, I'm hesitant. I'm not answering right away because I want to think does it make sense or not, right? Offhand, it doesn't make sense, but because absolute zero just means something isn't moving. So what does that mean? It's not moving. It's not moving. So you could, I guess what you're asking is, could you say, if you measured the velocity of it, would the velocity and energy be related in the same way? And that, of course, is something you could ask. We don't measure, we assume the velocities, but we don't actually measure the velocities of antihydrogen. But for the antiprotons and the positrons, people can measure that. And that does come out to be pretty good.
Thank you.
But I don't think that's the same as saying absolute zero, quite the same. But you could ask all sorts of questions, you know, but for antimatter and matter, as far as anybody knows, the kinematic equations are correct, which would relate velocity and energy. Okay, so we are not alone. I've described everything we're doing, but we have competition. Actually, this competition, ATRAP gave up, so we have less competition. There's Alpha, Asakusa, Base. Elena provides the antiprotons, extremely low energy antiprotons, Elena. G-bar is a gravity experiment. Base takes, they actually have taken one antiproton and stored it for over a year, studying its properties. So by studying it for a long time, they can get very good results on their properties. And this is, so to give you a size, this is the antiproton decelerator at CERN. And maybe this is the size of 2 football fields, sort of cut it like this. You got a football field, so 1 and 2 of that order. Okay, this is just an example. These things can't be done without the help. And this is this typical, there's a Dana, Mike, my colleague Joel Fajans. Will Bershey is now spokesperson for the gravity experiment. He was a graduate student here. That's Hughes. Celeste Carruth is now postdoc elsewhere in Europe. Delilah Ribeiro is a graduate student at Santa Barbara currently. So in summary, we can routinely trap 1,000 per day. We intend to study CPT. We'll improve all our measurements by a factor of 10. And if we see something, our first instinct will be not to believe it, but maybe it'll be true. So we'll measure it again and again if we find something exciting. Nobody's ever done antimatter studies like this before. Nobody's been able, we're the only group that can make antihydrogen reliably and store it and measure it. So we have the sort of the world to ourselves, at least for the time being. One of the game plans here, this is done in the AD hall, as I showed you. That's not a great place to do precision science. People are talking about ways to take antihydrogen. In the same vein of the movie that I showed you, right, Angels and Demons, people would like to take antihydrogen, put it in a container, and move the container over to a different laboratory at CERN, where they can do really high precision experiments, where they can combine the antihydrogen with all sorts of other atoms and make all sorts of other interesting measurements of fundamental properties of materials. So the game plan then is to make, not only improve our precision, but people would like to make movable antihydrogen so they can actually play with it elsewhere. And again, so if any of you come to Berkeley, we are always sending undergraduates there. This is the last slide. So from Berkeley to CERN, this is just one summer, and this is another summer of students who went to CERN as undergraduates. I guess there are a couple graduate students in the bottom picture who went to CERN to study with us. I am more than happy to answer any and all questions about this or about the other things that I do. Thank you so much.
I have two questions. This is Dan.
Yes.
I came a little late, so it's possible you might have covered this. The first question is it possible for your antihydrogen to have the equivalent of an anti-neutron in it and not just a proton?
Okay, so that's an interesting question. So you want to make anti-deuteron or anti-tritium or something?
Sure, why not?
Why not, right? Or a neutron with it, right? Okay. The answer is that it would only have protons because in the process by which you make, first of all, nobody knows of the process by which we make the antiprotons would not make a proton with a neutron or a proton with an antineutron together. These things are made at high energy and they all come out separately. So the antiproton is then decelerated. It's bent around a ring, and the radius of that ring is determined by the momentum of the antiproton and the magnetic field. Or more precisely, if it has the wrong momentum, which it would have if it had twice the mass, which it would have if it had a neutron, it wouldn't be able to go around the ring because the magnetic field, the magnetic force wouldn't be strong enough. But I like your question because it brings me to something I wanted to say, which is that in experiments at Brookhaven, they have seen anti-helium, but they're made at very, very high energy. So they can see a higher energy anti-nucleus when they collide. I guess they're colliding heavy ions together. It's the relativistic heavy ion collider, RHIC. And they do see a few anti-nuclei of low number. But no, it should not have a neutron.
Cool. I have a second question.
Yeah.
And in my travels, lay studies of science, I recently discovered as an adult that regular old nuclei are actually part antimatter, at least in terms of brief periods of time, where there's some process that happens in the nucleus where for a brief period of time bits are antimatter.
Right.
And I think it's called pion exchange or something like that, if I remember correctly. And it made me wonder, since you're talking about anti-atoms, would a similar process be at work in an anti-nucleus, where it would be, for a short period of time, it would be regular matter?
Okay, so you're talking about the virtual pairs, and so I think you're talking about the virtual pairs.
Yeah.
In the nucleus, you would get so the nucleus. An electron is a fundamental particle. As far as we know, there's nothing inside an electron. It's just an electron. But a proton, as you know, is a composite particle, and so it's composed of 3 quarks. But beyond that, you have these virtual pairs that appear and disappear, and they in fact contain some good fraction of the mass. They appear in equal amounts, matter and antimatter. And so the hypothesis would, of course, be that, yes, what you're saying is right. You would have virtual pairs of matter, antimatter in the antiproton as well as in the proton. That's one of the reasons, in fact, that people believe that gravity will be the same for it's one of the indirect experiments. The people believe gravity will behave the same way with antimatter as it does with matter, is that when you take different isotopes of different atomic elements, or look at different things that have the same mass but different amounts of, you expect different amounts of antimatter pairs, then you see them fall at the same rate, you then conclude, at least as the virtual matter pairs go, that it's all the same. And that's a reasonably high precision, better than the 10 to minus 2 that we're going to get. So that the indirect experiments exactly use that physics that you're talking about to say that you expect antimatter and gravity to be the same as matter gravity. But it's not quite the same as doing the tests that we're doing, in the sense that ours is very, very clean and precise. And you don't have to make any assumptions about these virtual particles.
Cool. Thanks. I appreciate it.
Sure. Other questions?
I have a question.
Sure.
For the up quarks and down quarks in the anti-proton, are the charges flipped?
Yeah, so it's the anti of each of the, take the anti of each of those quarks.
Okay, thank you.
I have a question.
Yes.
I might have missed it earlier, but you said that, or if hydrogen is actually neutral, then how are you trapping it between the magnets? Why is it reacting to the magnets if it's
Excellent,
neutral?
excellent question. Yeah. So let me go back to one of my slides here. Just a sec. Okay, can you see this slide? You see a slide with a little bar magnet in it now?
Yeah.
Okay, so I turn this on. The positron, so electrons and positrons have something called spin. Spin is basically gives it a magnetic moment like a bar magnet has. And therefore, if you were to take a bar magnet and put it in our trap and give it a little kick, you would see that it would wander around the trap kind of like this bar magnet wanders around this trap. So this is a cartoon of what we're doing, but it's exactly that physics. The spin acts as the same way a bar magnet would act, and I'll just play that again as a talk. And the antihydrogen is confined by a magnetic field gradient. So in the same way, so if I put a bar magnet in a magnetic field, so the north will go to the South Pole and so forth, right? But so the magnetic field were uniform, it would just align itself, but it wouldn't move with the magnetic field. It moves because the magnetic field is stronger in one place than another. And so basically what happens is that with the correct alignment, it's a little more complicated than I'm telling you. It aligns in some way with respect to the field, and we can only trap half of them. The other half are aligned in a way in which they're untrapped. But if you think of this in terms of energy, as it goes up towards the walls or towards the ends on the left and right, its magnetic energy, which is the magnetic moment dot product with the magnetic field, increases, and therefore energy is conserved, and so its velocity has to go down, and then it will just bounce back and forth. And that's why we need low energy ones, because if they're too high in energy, they climb right over the magnetic field wall, which is what you see at the bottom here. This little red here, that's where we make antihydrogen, and then the antihydrogen itself has a little bit of longer extent, moves around here, but it hits the wall and it bounces back and forth. So we make a magnetic wall, and the extent to which we can make a good wall is technology. So this magnetic field here is in Tesla, and you can't make these are superconducting magnetic fields. You can't make magnetic fields with these kinds of gradients much higher than we're making them. We're at state of the art when it comes to magnetic fields. So that was one of the constraints of why we had to get such cold antihydrogen. Aside from doing the precision physics, we can't even trap it if it's not cold, because its energy is its kinetic energy would be more than its potential energy, and it would leave our trap. Same way, if you take a marble inside a bowl and you give that marble too high in energy, it's going to fly outside the bowl. The deepest bowl, magnetic bowl that we can make is governed by technology, and that's basically setting the energy for trappable antihydrogen. What we'd like to do is make a very, very weak bowl where the thing is barely moving, and then we get to high energies. We get to high precision, rather. Other questions? Did that answer your question? Other questions?
Yes, thank you.
I have a quick question. I may have missed it earlier, but if we were doing the prop to measure the gravity, wouldn't the magnetic field interfere with it, since we're using magnets to trap it? Or do we just disable the magnets once we do the drop? Or
yes, that's exactly what we do. Let me just show that again. I might have gone too fast. Okay. Okay, so here it is, yes. So that red is meant to be the antihydrogen, the red dot going back and forth. The mirror fields, it's a magnetic mirror. A mirror just means that it's pushing it back and forth, are top and bottom, they're set at 1 Tesla. And as I change that value, just as you suggested, 0.9, then the red particle can go further towards the mirror. 0.8, it goes further still. 0.7, it goes further still. Now it can bounce out a little bit, and eventually it comes out on the bottom. So yes, we lower the idea is we lower these mirrors until you get to 0, and we see if things come out at the bottom or the top. More precisely, what we want to do is want to balance the mirrors. So we have other fields that I'm not showing you. So we want to eliminate gravity as a force by canceling it out as best we can magnetically, and then seeing if things go up and down with in equal numbers. That's the actual experiment we're going to do. And that, even with our current trapping, we should be able to get a precision of plus or minus g. So it doesn't go up or fall up or down. We should be able to do that in the next, either this year or next year, assuming that we don't have some technical problems.
Okay, thank you.
I have
Other
another
question.
question. I have
Yeah,
another question.
sure.
You mentioned that, you're able to do these experiments, and there are certain aspects that you are technology limited, and then specifically you mentioned the magnetic traps. First of all, are there other aspects that you're technology limited on? And with respect to those, like, what is the rate of change of that technology over the course of years or something like that? I mean, maybe there's a Moore's law with this stuff for all we know, and that would enable you to do like another, just a completely different class of experiments in X number of years, say.
Okay, so great. We're limited certainly by technology in the magnets, and those are sort of material limits. If you to get a certain size magnetic field, you have to apply a certain amount of current. That current gives you certain forces on the magnet, and so those are material constraints, and they're pretty hard to get around in the sense that I don't see any Moore's law helping us there, because it's very hard to confine very, very big forces, basically. The lasers that we're using have been improving quite a bit. So when we started, we didn't really have the kind of lasers we have now. So there's been a lot of advances in laser development that we use, for example, for the cooling. I'm not a laser person, so I don't really discuss it in any detail because I'm not terribly knowledgeable, but the tremendous advances in laser technology, which we use for cooling. Greater advances in that would lead to better cooling. That's one possible area. I don't know if it's a Moore's law, but it's an area where we can get improvement. Some of it is cost, of course. The kind of detector you like might cost too much the bigger experiment it is. Bigger is your experiment. CERN has invested a lot of money in a new, that ELENA low energy electron ring, extremely low energy electron ring. So that's, instead of handing us electrons at 5 million electron volts, that's some amount of energy, it hands us electrons now at basically closer to 100 kilovolts, so a factor of 50 less in energy. So what that means is that we're going to be able to trap many more antiprotons. We're not exactly sure how to handle that greater population, but it should allow different experiments. One big advance that we had was that when we learned how to trap efficiently, I shouldn't say efficiently, I'll give you the numbers. CERN in 2018, the last year we ran, because CERN has this upgrade, every time they give us antiprotons, they give us maybe 10 million, but of those we can only trap, say, 50,000. So we're already losing quite a bit. Of the 50,000, maybe we're making 100 antihydrogen. So you can see that the numbers are falling very quickly here. So we could certainly improve our antihydrogen trapping numbers to the extent we can turn that into better physics is the question that we have to answer. And one of the ways to do that will be to actually find ways to take these things, at least I think, speculation, take the antihydrogen, put it in some kind of a box, and move the box to a laboratory where you can do higher precision physics. But again, that part of it is like the God particle and all that in the movie was silly, but the idea that you have a trap and the trap needs electromagnetic fields, and if your battery wears out when you're moving them, you're sunk. So that's true. But I would say that one big advance will be doing new clever experiments. So which would be taking these to a different place and doing some clever experiment that people haven't thought of yet, or maybe just haven't done yet. So I don't quite see the Moore's law, but helping us anywhere. But I do see trying to be clever, trying to have more people do it. Right now, we're the only ones that make antihydrogen. I think the more groups that make it, the better off the field is, because it's just people think differently, and it's good to have competition. So, you know, while it's nice not to have anybody trying to take our space, it would be much better to have more groups doing this on a regular basis. And right now, to do this, you have to be in the AD hall. You have to be at CERN in this place, some place in the world where you have low energy antiprotons. They've invested a lot of money over the years in this physical infrastructure. Did that kind of answer your question?
Yeah, it was open. It was open on purpose.
Okay, good.
I have a question.
Sure.
What are your thoughts on the matter-antimatter asymmetry? And why do you think the asymmetry was caused?
So you're talking about a CP violation, right? I assume you're talking about CP violation, which is what's measured to the 0.2%. I don't know is my answer, really. I mean, I'm you know, like most people, I probably, to the extent I expect anything, I don't think we're going to see CPT violated. But physics is, you know, if Madame Wu, as she's known, hadn't done her experiment, you know, people might have taken years and years later to discover parity was violated. I mean, that was a very fundamental thing that she did. It was, you know, it was a well thought out experiment, and it really changed the way people think about symmetries. And you understand that if CP is violated, that means T is violated, right? CPT is if you believe CPT, okay, as holding, and you violate CP, it means you should also be able to violate T. And in fact, in some experiments at the Stanford B factory, they have seen time violation, which doesn't even seem possible, but there you go. So I don't really know. I don't have strong opinions about it, and other than I think it's really fun to try to find out. This is really an experiment where if it's a small chance of a really important result. So we march on, but I don't, beyond that, I can't say. I don't have any bias, you know. I think it's really important to do these experiments without thinking that we're trying to prove anything one way or the other. We're just trying to measure. If it turns out to be like this, fine. If it turns out to be like that, that's also fine. So, you know, it's no skin off my teeth however it comes out.
Some people have theorized that that neutrinos might annihilate with themselves, and that's what caused the asymmetry. What do you think about that?
It's one of those theories. I mean, I think it's speculative, so I don't have strong opinions about these theories. Basically, there aren't any good theories even for why CPT should be broken. So there are many. So for example, for dark matter, so I assume physics club you've heard of dark matter. So there are a lot of dark. And did Dima Budker talk, or is he going to talk?
He's going to.
Okay, so Dima, my colleague Dima Budker, will talk, among other things, no doubt, about his axion searches, which is a search for physics beyond the standard model. And axions could be some class of axions could be solving the dark matter problem. And there you kind of have theories and limits. It's a slightly different flavor to the science, because you can say, I have this theory, I rule that out. I have this theory, I rule that out. We're in the stranger condition where there is no specific theory. I mean, there are some very specialized models which you can begin to rule out, but there's no kind of grandiose theory that says, you know, CPT should be violated if at some level, if you measure such and such, you can see if it is or isn't. So we don't have that kind of theoretical framework that we're working with. It's much more speculative, if you will.
Are there any other questions?
I have another question, I guess. For like the entire premise of the experiment seems to be like measuring like antimatter's relationship to gravity, and whether they fall at the same rate as say matter. Is there like have there been like if it is confirmed sort of by theories, would the experiment essentially be confirming or like seeing if the theory was right, or are there other like have there been other hypotheses on how antimatter can interact with gravity besides like say okay antimatter just acts just like matter with regards to gravity?
Yeah. So most theoreticians will say that matter, antimatter, and matter should do the same thing with respect to say the Earth. So that it should be the same. There are a couple of theories which predict something different, but I don't think they're terribly well regarded by. I'm not that kind of a theorist, so I can't say in particular, but I think most theorists would not subscribe to one of the theories that say gravity should be different from matter and antimatter. I don't think it's quite as speculative as the CPT violation. So I think there are probably more people who would. I think people might be less surprised about the gravity anti-gravity question rather than going up is different, but it might go down at 99% of G, right? So you know going up would be an extreme case, but some small violation there, something could be possible. Again, because there only are these indirect tests, and there are precision measurements of CPT in using different particles. So there are a few theories that allow for antimatter. Some of them have been theoretically disregarded already, but others I believe are still at least supported by the proponents.
Okay. So also I think I guess one more question. I might have missed this. But essentially basically you create the conditions sort of like to have it so that the antimatter doesn't decay during the like the sort of Pisa falling experiment, right? Yeah.
Mm-hmm. Yeah.
That done through like cooling of some sorts.
So what we do is we'll make it as cold as we can, but even without the cooling, we can tell up from down. We should be able to tell up from down. It doesn't decay because we don't allow it to hit the walls. That's our trick. So we make it with sufficiently low temperature. We can trap it without cooling it, which we've been doing. The cooling is only recent. The cooling will allow us an increase in precision of a factor of say 10 from where we were in 2018, maybe more depending on how well we cool. But the reason we could do it at all was that we could trap it in these magnetic bottles and it wouldn't get out. And so, for example, you have antihydrogen, it's a positron and the antiproton, you shine light on it. If you hit its resonant frequency, you kick the positron off, and now you have a charged antiproton and a charged positron, and they both hit the wall immediately. Because when you make the antihydrogen trap with the magnetic fields, you can turn off the electric fields, except for one bias field that would just shove out charged particles. So as soon as you get a charged particle in there, you kick it out. And if you ionize something by hitting it with the right frequency, you see it. And so that's how you do the experiments, is you change the frequency of your laser. And if you're at the right frequency, you kick something out. If you're not at the right frequency, you don't.
Okay, thanks.
Sure. I've really enjoyed this. I've been very impressed by the questions from the Berkeley High students and from the adults. So and maybe Berkeley High students are adults too, I don't know. But I thought the questions were very good. It's not easy to ask questions in a seminar, so I really I think the young ones here are off to a great start for college. Join a research group and ask questions. It's always a good thing to do.
Thank you so much for talking to us.
So
Yeah, this
totally
is
my
amazing.
pleasure. And I look forward to hearing of your great careers later.
I learned a lot. Thank you.
Thank you.
Okay,
Yeah,
thank
this
you
is
so much.
fantastic.
Take care.
You too.
Thank you.
Bye-bye.